Alright everyone, welcome back to another video here on the channel. Today we're going to be talking about polynomials. So first I'm going to explain what a polynomial is. Well, here's the general expression for a polynomial, and I've written it down here, but this might not mean anything to you, or it might just seem hopelessly complicated. So I'm first going to give you a few examples. You can think of polynomials as expressions involving x's to certain powers, but there are more restrictions than just that. Okay, so as a first example, we can have 5x minus 7. This is a polynomial. We can also have 10x squared minus 6x plus 5, or maybe root 2x to the 4 minus pi x squared plus 10x minus root 5. All of these are examples of polynomials, and you can see that what we have here are a whole bunch of terms that involve x's and they're added together. And for each of these terms, we have x raised to an integer power. So x to the 1, x to the 2, or x to the 4, as here. And each of these terms has a coefficient. So for this term, the coefficient is 5. For this term, the coefficient is pi. And there you have the essence of what a polynomial is. So going back to this general expression, essentially the an minus 1, all the way to a1 and a0, these are constants, and they're called coefficients because they are multiplied to the x terms over here. And n minus 1, n minus 2, all the way down to 2, 1, and 0, these are the powers of x's. And now you have the basic introduction to what a polynomial is. Alright, so next up we're going to cover some terminology connected with polynomials. First we have the term degree. So degree, you can think of it as the number that represents the highest power of x that exists in this particular polynomial. So for example, if we take 10x to the 4 minus 5x plus 3, the degree, denoted deg with brackets around this, is equal to 4, because as you can see, 4 is the highest degree over here. So the first term has degree 4, this one has degree 1, and this one has degree 0. And so the overall degree of this polynomial is 4. For something else like 5x squared minus 10x to the 5 plus 3, note that this one is not noted in decreasing order. We actually see that x to the power of 5 is the power of x is the highest, and so we have degree of this equal to 5. Of course, it is defined that the degree of a constant c is equal to 0. However, we have to be careful here because we cannot let c equals to 0. This is an exception because 0 is just a very special case. And if we define degree of 0 to be 0, we are going to run into problems later on. Alright, so next up we're going to talk about factors. You might have encountered this word already when discussing integers. So as a refresher, if we take the number 24 and we want to look at its factors, well, we simply have 1, 2, 3, 4, 6, 8, 12, and 24. Hopefully I did not miss any here. And what this means is that each of these numbers on the right divides into 24. So that's fairly simple. And there is a similar definition of factors for polynomials. So unfortunately for polynomials, it's a bit difficult to give a polynomial and then find its factors. So I'm first going to work it the other way around. So suppose we have this expression here. Now we can expand this out and get x squared minus 10x plus 21 times x plus 5, or x cubed minus 5x squared minus 29x plus 105. So if you have no clue how I just did what I did, don't worry right now. But all you need to know is that this first expression and this last expression are the same. So what we have here is that each of these terms is called a factor of this expression here. So similar to a number, the factors of a polynomial can multiply together to give the original polynomial, or some combination of them. It should be also noted that this expression here is also another factor, but it's not the most fundamental factor, because this factor gets reduced down to these two if you factor further, similar to how you want to quote-unquote prime factorize an integer. Alright, so now we're going to talk about the first theorem that we're going to encounter today. It is called the fundamental theorem of algebra. This is not a theorem that I'm going to prove because that is ridiculously difficult. But what it states is that if you have a polynomial of degree n, so let the polynomial be p of x, and the degree of it is n, then p of x has n roots. So this is the most basic expression of this. Taking an example from earlier, we had, I believe, x minus 3, x minus 7, and x plus 5, and we expanded this into an expression involving x cubed, and 3 is the highest degree here. So as you can see, if we set this polynomial to 0, what values of x satisfies this equation? Well, obviously it's 3, 7, and negative 5. Because take 3, if you plug 3 back into here, this first thing ends up being 0. So it doesn't matter what the other two are. The first one is 0, and thus the entire expression is 0. Same thing goes for 7 and negative 5. So what the fundamental theorem of algebra is saying is that if you have a polynomial with x to the n plus some lesser degrees, then this thing is going to factor into x minus r1, x minus r2, so on, x minus rn. So there are n roots, and you write it out like this, because if we set it equal to 0, you'll see that r1, r2, all the way to rn are the roots of this polynomial. But unfortunately, this theorem is a little bit more complicated than this, and I'm going to explain why. There are two main additional points that we have to be careful of. The first one is called multiplicity. So this is essentially when you have a factor that appears twice. So if instead of x minus 3 times x minus 7 times x plus 5, we had this expression. Well, you can also write this as x minus 3 all squared times x plus 5. You might say, well, this is an expression where the degree is 3, but we only have two roots, and that is 3 and negative 5. But the 3 is counted twice. This is called multiplicity. The 3 here is counted twice because there's a double factor of x minus 3. So if you have a factor that appears more than once, each of these factors are counted in this theorem. The other complication involves complex roots, basically roots of the form a plus bi, where I is equal to the square root of -1. If you have no idea what is going on here, it's alright. Essentially, this occurs when we try to solve stuff like this. Obviously, if you think along the real line, basically all of the real numbers like -10 or 1 or pi or root 2, there is no solution because the squares of real numbers are non-negative. Thus, such expressions have no real roots. But this expression does have roots, and they are complex roots in the sense that they involve this magical number here called I. So if you ever encounter such an expression and you think, there should be roots, I should be able to find them, but if you don't understand complex numbers yet, you might not be able to find them. But that is all that I'm going to cover about the fundamental theorem of algebra. If you don't really understand the two additional points, as long as you understand this portion here, you are good to go for today. Alright, so next we're going to talk about the remainder theorem for polynomials. And so here is the general expression of the theorem, and this is very similar to the remainder theorem for integer division. So taking an example, if we have, say, 35, and we want to divide it by 3. Well, when we first learn division, we see that this is equal to 11 remainder 2. But there's another way to write this that does not involve this weird symbol r. We can write it as 35 is equal to 3 times 11 plus 2. So 2 is the remainder here, 3 is the divisor, and 11 is the quotient. So the remainder theorem for polynomials is very similar. And similar to the theorem for integers, there's a restriction on what the remainder can be. And the restriction is that 0 is less than or equal to the degree of the remainder is less than the degree of the divisor. Now this is very similar to that for the integers, because for integers, take the example that we just did, we have that 2 is between 0 and 3, or 0 is included but 3 is not. And the restriction for the polynomials is just the same. So a really powerful extension of this theorem is if we take the divisor to be x minus a for some constant a. Then the theorem transforms into this. And see what happens when we plug in x is equal to a. The right-hand side of this expression is equal to r of a. And take note that with the restriction on what r of a can be, the restriction on its degree, since the degree of d of x is 1, with the x here, the degree of r is limited to being 0. Therefore, r of a is a constant. We can write this as c. So what do we have here? We basically have a very powerful method to find r of x for a factor that has degree 1. So if we have a polynomial and we want to find its remainder when divided by x minus a for any constant a, all that we have to do is plug a back into the expression for p, and whatever constant that pops out the other side is the remainder r of a. Alright, so this concludes our discussion of polynomials today, And I'm going to be back next time with some example questions involving these theorems and the basic properties of polynomials. Thank you for watching, and I'll see you next time.